Alright guys, let's see how we can solve question 19 from the chapter 7 of Hibbeler textbook Engineering Mechanics. And in this one we need to determine the internal normal force, shear force, and moment at point C. So basically we are trying to figure out the internal forces and bending moment at point C. So what we're going to do is that we have to find all the reactions that we have in the support A. And once we have that, we're just going to do a section at point C. And if we look at the free body diagram of this part of this beam, we should be able to find all the reactions and actually all the internal forces and bending moment at point C. But before that, let's just figure out what are the reactions at point A. We have a pin at point A, which means we have both X and Y components. So let's just draw the free body diagram for this part of the beam that is attached to the pulley. So first of all, we're going to have the tension in the cable in here where we can call it T. As I said, at point A, we have both X and Y components since we have a pin. We can show our X and Y in here. We have a distributed force on beam, which is going to be a rectangle. So first of all, we know that it's going to apply at the centroid of this beam. Sorry, it's going to be applied exactly at the center of this distributed force since we have a rectangle. So we have 8 plus 4, 12, which would be the length of this distributed force. So it's going to be applied somewhere in the middle. So 12 divided by 2 or 6. So this is going to be 6 feet. And same for the other side. And if we want to find the magnitude of the force, we have 150 pounds per foot, and the length is 8 plus 4, so we have 12 feet. So that's going to give us the total force in here. Let's calculate that. So 150 times 12. So 150 times 12 is going to be 1800 pounds. Or if we want to report it as kips, we're just going to divide it by 1000, 1.8 kips. Now we are in equilibrium. So we have sum of all forces equals 0, and we have the same thing for the moment. We're going to start with our moment equation because that way, if we do the moment about point A, we can get rid of all the unknowns that we have at A, and we should be able to find the tension in the cable, or T. So the T is going to make a moment counterclockwise, so it will be positive. So T times the distance would be vertical distance to the line of action, which is what we have in here. So it's going to be 2 plus 0.5, these two in here. So 2.5, and we're going to have the moment of the distributed force, which is going to be in this direction. So this one's clockwise. So negative 1.8 times the distance. Again, the distance from A to the line of action, or I should say the vertical distance. So it would be A to the center of this distributed load, which is going to be 6, equals 0, and we should be able to find the T based on kips. 1.8 times 6 divided by 2.5. So 1.8 times 6 divided by 2.5. That's going to give us 4.32 kips, which would be our tension. So now that we have the force T, we can use our sum of all forces in X direction, and we should be able to find our AX. So AX we consider, we assume that it's to the right or positive, so plus AX minus T is equals 0. Our AX would be also 4.32 kips, and our assumption for the direction was correct. And the last one is the AY, which we only need to do sum of all forces in Y equals 0, again because we are in equilibrium. So AY minus 1.8 is equal to 0. So AY would be 1.8 kips. No negative sign, that shows that the assumption for AY was also correct. Okay, now that we have the reaction at point A, we're just going to do our section, and we're going to consider this part. Let's just draw the free body diagram for it. So we found our AX and AY, 1.8 kips for X, for y, and our x was 4.32. And we're gonna consider normal force, let's call it NC, shearing force VC, and a bending moment MC. Regarding the directions, you can just pick whatever you want if you get a negative sign. It shows that our assumption was not correct, but like we are in equilibrium again, we're going to use our sum of all forces in x equals 0. So the normal force, we assume that it's to the left, so negative plus 4.32 is equals 0. Normal force would be also 4.32 kips, no negative sign, that shows direction was correct. Sum of all forces in y equals 0. 1.8 minus VC, and I forgot one thing in here. We have half of that, or I should say this part of the distributed force in here. So we are dealing with this rectangle, which has a side of 3 feet. So we have 3 feet in here. So we have the same force. It's going to be applied exactly at the center. So 1.5 on each side. And the force would be, so the load is 150 pound per foot. So it's 150 times, this time the length is different because we have 3. So it's going to be 450 pounds or 0.45 kips. So that would be another force that we have in y direction equals 0, and our VC would be 1.8 minus 0.45, which is going to be 1.35 kips. No negative sign. Again, the direction was correct. And last one is the bending moment. We're going to do the moment about point C, counterclockwise positive. We assume a counterclockwise bending moment, or our MC. So we have MC, we have the moment of the distributed load, which is in this direction, also counterclockwise, so plus 0.45, and the vertical distance to point C would be 1.5. And we're going to have the moment of our AY, which is going to be clockwise moment about point C. So this one's negative 1.8, and the distance is the length of the beam, which was 3. Equals 0. Our MC in here would be 1.8 times 3 minus 1.5 times 45. So 1.8 times 3 minus 1.5 times 0.45. That's going to give us 4.725 kip foot, and that's going to be the bending moment part of this question and the final answer for this one. Hope everything was clear. Let me know if you guys have any questions. We are covering 3 different textbooks for engineering mechanics in this channel. Feel free to check out the playlist and let me know if you have any specific problem that you want me to cover in the next ones. You guys take care. I'll see you next video. Have a good one.